Can be mathematically modeled as a graph, where the vertices are neurons and the edges indicate which neurons are communicating during a given time slice. We can then interpret this graph as a simplicial complex by converting the complete subgraphs into simplices. But we can add one additional layer of information to this neural network: the direction of information flow. There's an inherent asymmetry in the way one neuron communicates with another. The electrical current passes from the presynaptic neuron to the postsynaptic neuron. We can encode that by adding an arrow indicating the direction of synaptic transmission on each edge of the graph. This is called a directed graph. A directed graph provides way more information than an undirected graph. Consider this undirected graph. It has 6 edges. What happens if we make it a directed graph? For each edge, there are 3 possible directions: this way, or both ways. That means there are 3 to the 6, or 729, possible directed graphs. When working with the undirected graph, we're collapsing all 729 possibilities into one. There's a lot less information encoded in it. If we consider information as flowing through the brain from neuron to neuron with a specific orientation, we're most interested in highlighting the graph structures associated with that directed flow. Let's say you have 4 neurons, all of which communicate with each other. We model them as a complete directed graph. In this case, there's one neuron from which all the arrows are pointing out, and one neuron toward which all the arrows are pointing. We call these the source and the sink, respectively. Last episode, we talked about how to form an undirected simplicial complex from an undirected graph by converting each of the complete subgraphs into a simplex. Similarly, we can form a directed simplicial complex from a directed graph, but importantly, we only convert complete subgraphs with a source and a sink into simplices. Let's see that in action. Here's the undirected version. Each of the 3 vertex complete graphs forms a 2-simplex, a triangle. Now, let's add some arrows to the edges. This 3-vertex complete graph has a source and a sink, but this one doesn't. So the resulting simplicial complex is different. The restriction of having a source and a sink means that our resulting simplicial complex has less higher dimensional simplices. But the ones that are there have a directionality. We're really honing in on configurations of neurons through which information is flowing, not just vibrating around randomly. We now have a theory about how to analyze a system of neurons. Build a graph where the vertices represent neurons and the directed edges represent synaptic transmission. Convert that graph into a directed simplicial complex and compute the topological invariants, like Euler characteristic and Betti numbers. Now it's time for the next step in the scientific method: test the theory. We need to ensure that this topological interpretation is actually helpful data, that it illuminates significant features of the neural structure. So, what sort of simplices are exhibited in the reconstructed brain? This shows the number of directed simplices of each dimension within the digitally reconstructed brain. The researchers checked several variants and found that the reconstructions consistently contained directed simplices of dimensions up to 6 or 7, with as many as 80 million directed 3 simplices. But what does that mean? How do we know if that's significant? If I draw a bunch of neurons and start arbitrarily adding edges, in other words, make the neurons fire randomly, we're bound to have some simplices, even some of higher dimension. Well, they checked exactly that. They built a random graph, called an Erdős-Rényi graph, with the same number of neurons, or vertices, and the same average connectivity. It's basically the graph of a random brain. And this shows the number of directed simplices of each dimension within it. There's way less, which is a good indication that all the simplices within the actual neural graphs aren't just noise, but an important organizing feature. In a static picture of the brain's structure, there are a surprising number of simplices. But what happens to these simplices when you look at a dynamic picture, if you watch the brain change over time? To find out, the researchers gave the reconstructed brains a stimulus and recorded the shape of the neural network at little time slices. How did the simplices and simplicial complexes change over time? In the graph representing connections between neurons, this is the number of edges as time passes. Viewing this graph as a simplicial complex, these are the first and third Betti numbers and the Euler characteristic. They grow and then shrink. This happened with several different models and different stimuli. Here's another way to look at it. Each patch of this swoosh is a little time slice. Shortly after the stimulus, it starts here and builds up, and then collapses back down. The axes are showing the first and third Betti numbers, so it's showing you how many holes of various dimensions the brain's simplicial complex has. In response to the stimuli, the neural network builds up this complicated and high-dimensional structure and then collapses the whole thing. These intricate simplicial complexes seem to develop in response to neural activity. The simplicial complexes highlight a clear pattern in the structure of connections among neurons, a pattern that will hopefully illuminate the connection between this structure and its emergent function. The next step in these researchers' investigation is to create these topological models of a system of neurons as it's learning a task, and see how learning changes a brain's simplicial complexes. It's impossible to know how fruitful this approach will be, but without the tools of algebraic topology, we wouldn't even be able to see this pattern or analyze it. Topology provides a sort of filter to shake through the seeming chaos and reveal structure. And neuroscience isn't the only place where topology is finding practical application. Topological data analysis is a thriving new field which uses the tools of topology, remember the ones that are good at counting and collating holes, to study the shape of high-dimensional or noisy data in areas like image analysis and material science. It can be tempting to dismiss an 11-dimensional triangle as a goofy mathematician's construct. But part of the beauty of mathematics is, as Eugene Wigner said, its unreasonable effectiveness in the natural sciences. Throughout history, even the most abstract mathematics eventually finds its way into our concrete physical world.